Welcome to the Neural Networks project, and in this project we're going to look at the building blocks of neural networks, a recently very popular method for dealing with high-dimensional data, such as language, translation, handwriting, that kind of thing. Things where you have a lot of dimensions to create relationships between your input and output. The building blocks of a neural network go back to the perceptron, which was an invention of Frank Rosenblatt and others in the late 50s. And they had looked at biological work being done, a lot of it with whale neurons, giant whale neurons, trying to figure out how neurons worked generally by looking at really, really big versions of neurons. So they saw this work and they thought, well, maybe we could build a computer that represented the same kinds of ideas that people were learning about from these giant neurons. So they devised simple computational devices made up of inputs, here represented by x1, x2, x3, and then a threshold, and then an output represented by O. And the idea is if you get enough inputs to overcome the threshold, then you will get an output. Otherwise, you won't. So the next kind of way that they could kind of modify and work with this very, very simple model was to add weights to the inputs. So not all inputs would be worth the same amount towards reaching the threshold. And that allowed them to get a lot more control and apply the perceptron to more complicated data. It also allowed for a mechanism to use the weights to model the relationships more precisely between inputs and outputs. So let's have a look at that now. Here's our simple perceptron. We've got a bunch of inputs, and then we've got a bunch of weights that feed into the threshold that give us some kind of output. So what would an example of this look like? We could look at whether or not you might attend class. So let's say the inputs are whether you find the topic interesting, yes or no, whether you're feeling well or not, yes or no, and whether your friend is attending, yes or no. If we make the threshold 2, then we need the inputs to exceed that threshold, and if they're all weighted as 1, then they would all be weighted equally. So in this case, we would need at least 2 of these things to be true for you to attend class in this model. We could adjust the weights, or we could change the threshold. We tend not to change the threshold because that tends to be a very gross way to control the neuron, and it's much more fine-tuned if you use the weights. So another way of talking about the threshold is it's called the bias, and often it's represented as a negative number, and the inputs are represented as positive numbers. So the positive numbers have to sum above the negative number. This allows us to talk about the perceptron firing and how easy it is to make that perceptron fire. What Rosenblatt discovered, so why he thought that this was an interesting problem, was that he saw that you could actually create what's called a NAND gate from a perceptron. So a perceptron could act as a NAND gate. And a NAND gate is a gate that opens whenever there's anything going through it, but if all the inputs are open, then it will shut. So it is a logical gate. And the importance of the NAND gate is that you can actually derive all other types of logical Boolean logical gates from a combination of NAND gates. Now, I'm not going to go through how that happens, but if you're interested, you can look up the Nielsen 2016 reference. They have a nice diagram of how you can derive all other logical statements from a series of NAND gates. So we can use the perceptron to do very basic classification. The classification has to be linearly separable. So what I mean by that is if we look at this diagram where we have circles on one side and triangles on the other, if something is linearly separable, you can draw a line between the two groups easily. If they are mixed up or they form a circle or something like that, they are not linearly separable, and without further modification, a perceptron won't work. But for linearly separable classification problems, you can use a perceptron. And the way it would work would be like this. So we have a simple perceptron with x and y inputs, and those x and y inputs are going to be weighted in some way to reach a threshold value or a bias value and fire an output, and the output will be either that you belong above or below the line. So we can start off with our arbitrary set line here, and that line, if we rearrange the input and weights, we can derive a formula for that line. We always have one more input than the number of inputs we have, and one more weight than the number of weights we have to make the math work. So that's kind of our intercept if you're used to looking at linear relationships. But here we can see that this particular line actually misclassifies one of our triangles. One of our triangles has been put below the line and it's not with the rest of its friends. That's no good. We want it to belong with the rest of our friends. So how do we update our model in order to make it better? And that is pretty simple. We can use this formula. So if we take our misplaced triangle, we can update the weights in order to change the line so it better reflects this data and hopefully pushes the triangle on above the line where it belongs. So the way we do this is using this formula, where we take the old weights and we add to them the learning rate multiplied by a reclassification multiplied by the original input. Now the learning rate is the amount by which we want to modify our line in one single step. So we're going to update one step now. The bigger that number, the faster we will change, and hopefully the faster we will find the correct line that classifies everything correctly. But it also means we can overshoot if our learning rate is very high. If our learning rate is very low, then it's less likely that we will overshoot, but it will take longer and it's probably computationally more expensive to get there. So there is a trade-off there. But let's go through the calculations. In this case, what we want to do is take the old rate for our intercept, and the old weight was 0. And then we're going to add to that the learning rate, which here I'm using 0.2. And then I'm going to multiply that by the reclassification, which is 1, because we want the triangle to be above our line. And then we're going to multiply that by the original input. And for the intercept, that is 1. And so we get a new weight of 0.2. And if we make those calculations for both our x and y weights, we end up with new weights of 1.4 and 0.1, which we can rearrange into the equation for the line of y equals minus 14x minus 2. And then what we end up with is a new line, which is admittedly poorly drawn by me, but it means that the triangle is well within the top group. So then it only took one step to get there. We could have had a smaller learning rate, and then maybe it would take a few steps, or a larger learning rate, and we might have overshot and included some of our circles on the wrong side, in which case we'd have to go back. So you can see then that if your learning rate is too high, you can end up just flipping between misclassifying different points. So we don't want that. So choosing a learning rate is actually a difficult and usually empirical process. So it turns out that actually, even with only tweaking the weights, we still end up with very kind of gross input-output behavior, which can be a little bit hard to control. We end up with very big changes for very small learning rates even. So a way to deal with this is to actually change the output from a yes-no to a continuous value. And we do that by applying a sigmoid function to the output to convert it from 0, 1 to a continuous value between 0 and 1. So here it is. We're going to take our output value and we're going to apply this function, and that's going to smooth out the output. So it means when we update the weights and maybe the bias, we get less sudden changes in output behavior, which makes it more predictable. We don't have to use a sigmoid function. There are other functions, but it just turns out that the sigmoid function tends to be the most popular. Now we need to recognize that instead of getting a 0, 1 output from as we got with the perceptron, we're going to get a continuous 0, 2, 1 output. But the problem with that is that we are going to lose some interpretability when we do this. The 0 to 1 output, it's not a value that represents anything in particular. It represents the accumulation of weights, which themselves, it's unclear what they represent after you've kind of updated a lot. And this is one of the major complaints with neural networks. They are a black box. They often work in applied situations, and they work really well, but we don't understand why they work or what the weights or the outputs necessarily mean. So there is ongoing work on trying to make them more interpretable, but for the moment, they tend to be a black box solution. This becomes even more apparent when we start to string a lot of sigmoid neurons together to create a network. Here is a feed-forward network that models whether you're going to attend class based on lots more factors. And we have now 3 layers. We have an input layer, a hidden layer, and an output layer. And very briefly, the role of the hidden layer is in fact to represent the relationship between the input and the output. You can have many input layers to do this, and you can have many neurons in that input layer. Usually how many is an empirically determined thing. There are kind of best practices for different problems, but there's no unifying logic that can tell you exactly how many layers you should have or how many neurons should be in the hidden layers. It is kind of something that you just tweak and figure out by trial and error. So in this project, what I want you to do is to build a neural network that predicts whether a student is paying attention from their webcam footage. And you have the data available to you, and you have the package. And the package and its commands are explained in the RMD file. So good luck, and I hope you learn a bit about neural networks.